Hello and welcome back. This is Systems Design 522, the Fundamentals of Artificial Intelligence, taught at the University of Waterloo in the fall of 2023. And this is Lecture 8, the second part of Backpropagation. Okay, so in the last lecture, we introduced multi-layer perceptrons and the backpropagation learning rule that can be applied to learn the weights of these multi-layer perceptrons. And the core idea is let's just apply the same structure as a perceptron over and over and over again. But then once we do that, we're going to need a slightly different learning rule than the original perceptron learning rule. What do we mean by applying it over and over and over again? Well, the idea is going to be that we've got some sort of raw input X. We're going to build up features out of that raw input, and we're going to build up those features by doing weighted sums of those inputs, and then applying some nonlinearity. Then we're going to build up new features out of those features, and then we're going to build up new features out of those features, and then we can actually produce the output. And at each of these layers, what we're doing is we're always saying, okay, my new set of features is just going to be my previous set of features times some weights, and then apply some function. And then, of course, the big challenge is how do you learn these weights? And then what we showed last class is, well, we can learn them just using the standard approach of defining an error signal, taking the derivative of that error signal with respect to the weights, and that tells you which way to adjust the weights in order to decrease the error. That's exactly what a derivative is, right? It's as I change one thing, how does that affect something else? And so given that sort of definition of error, where we have some sort of target output value that we want, and we do some sort of error that says, all right, minimize the mean squared error here, or minimize the squared error here. We take the derivative. We just use chain rule over and over and over again. It was just, all right, fine, I implement, this is just how I have to go ahead and take the derivative. I'm just following sort of standard calculus rules. And we end up with these learning rules where the learning rule to adjust one set of weights is sort of dependent on the activities here, but then it's also dependent on these weights and is also dependent on these weights. But it's got this nice form where whatever error I've learned to compute this, I can sort of use that parts of that same math when I'm computing this layer, and I can use parts of that same math when I'm computing this layer, and so on. And so I can start at this end, go compute update my weights, and then reuse a lot of those calculations as I propagate that error backwards. Awesome. Okay, so that was the whirlwind summary of the previous lecture. What do we want to do now that we've sort of established that this thing sort of vaguely works? Well, one thing that might be kind of useful is to sort of start getting some sort of intuition about, well, what are these features that are being learned? We showed that it's capable of learning some sort of cognitive-ish type things in the previous lecture, things like that, learning a family tree. But like, can we get any sort of other mathematical intuitions about what's going on here? So, like, can we characterize what this feature is based on these other features? And one thing that we can point out is, well, of course, this is clearly going to depend on this nonlinearity. All right, so we're going to do some weighted sum. We have to apply some nonlinearity. What nonlinearity are we going to pick? Terminology. Sometimes this function here, well, I've been using g and I've been using f in order as a variable. Fine, both of them are quite common. Sometimes it just gets called the nonlinearity, just because we need something that's not linear. Otherwise, as we showed in the last class, having multiple layers doesn't give you any more advantage than if you had just one layer. So you need something nonlinear. So this is often just referred to as the nonlinearity. It can also be called the activation function, so the function that takes the sort of the activation, or how, this weighted sum of inputs, and then turned it into, well, how active is this feature? So sometimes it's called an activation function. But what sort of values are common? Sort of the most common, the one that was certainly used in the majority of the sort of early papers, and sort of was the most common thing that people used for a very long time, is this function here. So this is called the sigmoid, or the logistic sigmoid. This is a function that sort of, okay, for very negative values, outputs a 0. For very positive values, outputs a 1. For value of 0, it outputs a 0.5. And it's got this sort of nice smooth shape between. So why did people pick this particular function? Well, one reason, well, okay, so there's certainly, when they were developing this algorithm, they were certainly very inspired by the brain. And one of the things that was clearly noted in real brains is, well, when you take a look at what brains are doing, you tend to have these little components where you stimulate them more and they will be more and more and more active, but there'll be some sort of maximum activity that they won't go up more than. And if you don't stimulate them at all, then they just eventually start doing no activity at all. But they don't really go negative. You don't really have negative activity of a neuron in a brain. So it's got this kind of shape of, all right, I want 0 for very small values. So that's sort of like, all right, if I don't give this neuron any stimulation, the neuron doesn't do anything. For very large values, it'll have some sort of maximum that it'll hit, and fine, we're calling that maximum 1. In the brain, it'll be some sort of maximum activity level, whatever. And we've got something sort of kind of smooth in between. So that's one reason to pick this function, is it's got that sort of shape that sort of like feels kind of biological-ish. But the other big reason that they picked this one is it's got a really nice derivative. Why does that matter? Well, in the backprop learning algorithm, the derivative of g shows up all over the place. It's this extra factor that the chain rule just says I have to include all over the place, and so I better have a function that's got a really nice derivative to compute. Does this have a really nice derivative to compute? Well, it just looks ugly. Like, oh, I got to take the derivative. Oh, it's like there's this special quotient rule thing that I vaguely remember from calculus. That's like, I've got to do, all right, the derivative of something that's a fraction. I've got to take the derivative of I've got to take the bottom thing, multiply it by the derivative of the top, and subtract the top thing multiplied by the derivative of the bottom, and then multiply all that by the square of the bottom. It's just, fine, all right, let me go do lots of wacky math there. So, the bottom, 1 plus e times the derivative of the top. Okay, well that's 0, because derivative of 1 with respect to a is 0. Okay, so that term at least goes away. And then we've got f of x, that's a 1. The derivative of this, g prime, okay, so it's derivative of this with respect to a, that goes to a 0. E to the minus a, that's going to be minus e to the minus a. The minus sign multiplies by the minus sign, so we get e to the minus a on top. Sweet, all right, fine. And then the bottom is just the square of the original thing. Fine. Really? That's a nice derivative? That doesn't look like a nice derivative, but okay. Why is that a nice derivative? Well, it's a nice derivative because I can do a little bit of algebra on it. So the derivative of this thing, fine. I can just, expand out that squaring. That's these two components. Fine. Why would I want to do that? Well, fine, I can write this as in two parts. I can split this into 2 parts. Oh, and this first bit here, oh, that's kind of nice because that is just this. Right? If I've already calculated this, sweet, then I can just write this part just like that. Now what can I do over here? Well, that's kind of ugly, but I could do one of those sort of play around with the fraction thing by adding a 1 and subtracting a 1 at the top, so that, those two things can now cancel nicely. And now I can do, okay, this turns into a 1 minus 1 over that. Ooh, and that is something that's something we've had already. Sweet. So if I've already computed the activity of this neuron, I can also compute its derivative really easily. It's just the activity of the neuron times 1 minus the activity of the neuron. Okay, so we've got a really nice, easy to compute derivative. Okay. So that was sort of why this particular activation function has become very, very popular. I've got to compute derivatives anyway, may as well pick one that's a really nice, easy thing to compute. So that was the standard. Nowadays, not really. So really, you'll use that in sort of very rare circumstances if you really want to make sure that a feature only has values in 0 and 1. But there's another option now that was figured out, because well, there are other functions you could pick that also might have nice derivatives. For example, this is probably the most common nonlinearity that's used nowadays. This is the rectified linear unit. This is just simply, hey, do that sum. If the sum works out to a value less than 0, then set the output to 0. Otherwise, just use that sum. All right, way simpler to compute. There's none of this e to the anythings. It's basically just the linear do the weighted sum, and then the only thing I'm doing is I'm stopping it from being negative. This is why it's called a rectified linear unit. And one really nice thing about that function is the derivative is really blindingly easy. The derivative of that is just 1 if x is greater than 0, and 0 if it's less than 0. Really, 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 really simple derivative to compute. This particular function sort of got popularized from this particular paper here, Deep Sparse Rectifier Neural Networks. It's sort of interesting that this sort of, this sort of change sort of made a fairly significant improvement in neural networks. So basically, if you're ever using a neural network, try this first. And it's generally a little bit more well-behaved or easier for it to learn. Interestingly, as they point out in this paper, it's actually a better match to biological neurons than that sort of very, very smooth gradation. Way faster to compute, and just seems to get better performance in lots and lots of different tasks. That sigmoid was sort of standard starting in 1986. This particular paper that sort of just pointed out, hey, this is just better, actually didn't come out till 2011. So there's a long period of time of people using something that was sort of pretty and had that nice shape. But this going back and looking at a lot of those earlier results, you probably would have gotten better performance just by using this small other change. I will note 2011 is about when neural networks start getting incredibly useful for industry. So there's a lot more effort being put on to making them better and better and better. So there's a reason that there's a lot more attention got put on them right around then, and so optimizations like this started appearing around that point in time. But nowadays, just use rectified linear units. Fine. Okay, so that's what we're going to be using. All right, there's lots of different ways of writing it. Here's another way of writing it. So that's my particular function. I'm going to add up my features from my previous layer, do weighted sum of them, and take the max of 0 in that. However you want to write it. Let's see an example of what sorts of features this sort of system might learn. And we're going to do an example of the simple XOR task. So here's my training data. I've got 2 inputs and 1 output. And if my inputs are 0 and 0, my output should be 0. If my input is 0 and 1, my output should be a 1. If my input's a 1 and a 0, my output should be a 1. And if it's a 1 and a 1, then my output should be 0. And I'm going to make this really simple little neural network. We know this can't be done with a single layer because it's not linearly separable. All right, we sort of have tried to do this sort of task in the past, and we sort of had to introduce extra features. What we're going to do here is we're going to say, all right, we're just going to introduce 2 features, but we're going to let the neural network learn those features. All right, and then sort of to depict what's going on here. So here are my inputs, x1 and x2. The 4 dots that you're seeing here, those are my 4 points. That's my training data. And then once I've got the trained network, I can go ahead and feed in any x values, and we can see what the heck it actually does. Okay, and that's what I'm going to go color each of these different points. I'm just going to try every single possible input, see what the output y is. And then this is, and I'm going to randomly initialize these weights, run the network, and right now the network just classifies everything as blue. It's like, all right, so it's an output of 1 for everything. Clearly, it's just not doing a great job. But now we're going to apply this learning rule iteratively. All right, so we apply the learning rule. It adjusts these weights. It adjusts these weights. All right, we're a little bit better. We've started classifying this one correctly. This one's still bad. These are all still bad. We do it again. We do it again. Do it again. Do it again. And now we're starting to get a system that does a good job, given these inputs, it exactly perfectly classifies those 2 points and these 2 points, and does a reasonable job for all the rest of these points. Right? So that's what the sort of learning process is doing. And again, the only thing that's happening is we are slowly, gradually adjusting these weights. So it managed to find 2 features that it can use to combine together to produce the correct output. We know, because it's not linearly separable, there was no way of just doing weights on these original inputs that would produce the correct output, but it has created new features that it can use to build up this output. Of course, one thing we can do then is we can actually say, well, what do those features look like? Right? We could go ahead and say, hey, what if I plotted what this, how active this element is for all different possible inputs of x, and how active is this element for all different values of x? So what are the things that it is adding together in order to produce this nice output? Right. And what we can do, so if we go ahead and try that, then these are the 2 features that it learned. Okay, so this is a feature. So again, all it's got is some weights here. And this feature here, okay, is going to be, zeros for all this space over here. So for any of these inputs, that feature has a value of 0, and then it gets more and more and more as we go this way. And then same thing for this feature, over all this space is 0, and then we get more and more here. And then you can sort of see that, oh, right, I could add together this feature and this feature with some weighting. I could scale one of them, probably scale one of them by -1 and add them together, and I could get this graph. One thing to note about this is these individual features that it's built up, they're doing that sort of linearly separable, like these features, because they are just weighted sums of the earlier layers, these features must have this sort of linear pattern, right? So this sort of there's some sort of similarity, there's some sort of direction in space that this feature is very sensitive to. That is these weights. Okay. So there's what I'm pointing out here is there's strong restrictions on the sorts of features that can be learned in one particular layer, because those features are just a weighted sum of inputs combined with some nonlinearity. So they're always going to be fairly simple features that have this sort of nice linear structure. But then because we're doing multiple layers of them, now I can build up more complex features by combining together these earlier features. Okay. Of course, that was an example where there's exactly 2 features. And this is a nice case where, like, okay, given forcing it to actually learn exactly 2 features, now it's like, okay, I can then look at these results and go, oh, okay, I can sort of see how you combine this feature with this feature to get this answer. Let's go to a more complicated case where I just say same problem, but I just put 9 features in this layer and say, okay, go ahead and learn. Now you've got 9 features. What happens? Okay, well, again, it sort of does, after some learning, it goes ahead and does the task fine. It learned a different particular way of, it classifies the 4 points that it's trained on fine. We've got a slightly different pattern about how it'll generalize to new data, but that's okay. But then where the heck does this data come from? Well, that data must come from a weighted sum of these features. And this is what those features are. And looking at those things, it's really hard to build up how those, to visualize how those particular features, you can do a weighted sum of those features to build up this. Why are these useful? I mean, this feature here doesn't even seem to change at all across the input space. This is like an unused feature. We've got features that just, fine, they're all features that nicely divide the space, because they have to, because that's what this math says, that when I'm building up this feature I'm always going to get things of that form. But it's really hard to see exactly how these particular features can get added together to get this. And this is sort of a general problem with all of these sorts of neural network type things. Yes, they're going to find good features. There's no guarantee those features are going to be interpretable. Okay? It does tend to be the case that if we sort of make the network as small as possible, or small enough to do the task, then maybe it's a little bit easier to interpret the features. But there's no guarantee with that at all. That said, lots of people want to look at these features and try to understand what the heck it's doing. Even in that very first paper where they were looking at training up the network to learn about a family tree, you can do something somewhat similar. It's a little bit more difficult to sort of, I can't generate these sorts of plots just because here I can make these plots because there's only two inputs, x1 and x2, and I can just show all possible inputs. Here I've got a situation though where I've got my inputs are like this 24-dimensional, or no, more than that. It's like a 36-dimensional space of all of these sorts of inputs. Or I guess with these 6 features here. So again, from last class, this was learning the family tree. One of the inputs is what person it is. The other input is what the relationship is. These features here, for example, were built up out of weighted sums of these features here. And again, what they wanted to do is sort of analyze what the heck were the features that it learned that allowed it to figure out, to learn about this family tree. And one way they went ahead and did this is sort of tried plotting what the weights were between these inputs and these 6 squares. So that's what we're actually plotting down here. We're saying, all right, for each of these 6 squares, what are the weights between the learned weights between, say, this square and these inputs? The first square is this one, and then the second square, third square, fourth square, fifth square, sixth square. And going ahead and look at those weights, they can then say, okay, well, does that give us any sort of insight about what's being learned here? And there's a couple things that they at least did point out. So for example, one of these features turned out to be positive for all of this family and negative for all of this family. So one of these features seems to be indicating which of these 2 family trees is this person a part of. It's not just indicating that. You can see like there's magnitudes of these weights. It's if these weights were all -1 for one of them and all +1 for the other one, then that's all that would be encoded in that feature. But it is at the very least doing something like that. There's also weights like features like this one here, where it seems to be doing something about where in the tree the person is, but is being agnostic about whether or not it's one tree or the other one. Oh, sorry, I didn't mention the order that these squares are put in. Sort of important there. So the order that these squares are put in, all the ones for this top row, that's about this family tree, and then the bottom row is the individuals for the second family tree, and they're organized, lined up and corresponding. So like there's a close matching from one person in this tree to one person in that tree. So they're organized in the same row. So that means that this particular one down here, this feature here, it's doing basically the same weight for this person as this person, and the same weight for this person as this person, and so on for all of the different people. So whatever it is, whatever that feature is particularly picking out has something to do with where you are in the tree rather than which of the 2 trees that you're in. Okay. So that's the sort of analysis that people can do on these sorts of weights to try to pick out, what is it that's being learned here. Of course, we can also do this sort of with more complex inputs. We can do things with, say, digit recognitions. We feed in an image of a digit, and the output is which digit is it supposed to be. This is the same sort of thing that you used in one of your assignments for this course. Fine, let's also figure out what features this thing learns once you train it up to do this task. And then again, what we can do is we can take a look at, well, what are the weights going into each of these features? Because that should sort of say, what sort of pattern is it that causes this feature to be very active? That's one way to interpret what these weights are saying. And if we do that with these 20 features, then we should be able to say, okay, how is it breaking down these digits into little components that we can then go ahead and learn. Go ahead and learn how to classify based on. And after training, when we have a system that does a great job at classifying these digits, these are the sorts of weights that we get. And we're like, well, that's really not interpretable at all. What features are being picked out there? Like maybe if we really squint at it, this feature here is something like a detecting of a 0. So like it should be active, fairly active whenever we're shown an input that is like a 0, but wouldn't be particularly active for other inputs. Because again, what the feature's doing is it's taking this input, it's doing the dot product with this input and its weights, and then if that value is large, then that activity is going to be large for that feature. So you can sort of see that fine, these maybe would give a high value, but what the heck is going on with the rest of these? Like none of these are not picking out, I can't interpret any of those. But yet it does the task well. It still classifies perfectly well. Again, this is just highlighting that whatever these weights are, nothing guarantees that these weights are going to be human interpretable. It's just finding features that will do the task. Cool. All right. So fine. It's learning some sort of features. It would be nice if these were interpretable. It's a little bit hard to be, to figure out really what these weights are, but maybe in some cases we can at least get some insights. But that's just sort of the way things are. Are there, what other things do we have to worry about when we're doing this backprop process? So I guess more sort of practical details when running backprop. What do you have to worry about? I already commented, hey, use rectified linear units as your features. What are other things that come up? One issue is that we do have to start with random weights. Which is a little odd because at least with like perceptrons and SVMs, a lot of times we could just get away with initializing weights to 0 and everything was fine. Why do we have to start with random weights? That seems like a weird introduction. Well, one of the problems is the learning rule for early layers of the weights involves multiplying by later weights. And if those later weights are 0, then that means we're going to set these weights to 0 and it's just not going to learn at all. And so we're going to generally have this problem that if, that weights near 0, we're going to make it, it's just not going to learn. Or we've got to, it's got to wait for these later weights to learn to become non-zero before these. It's just painful. And so generally just things work better if you initialize them randomly. But then of course there's this question of, well, what distribution do you want to randomly initialize them from? Initially, like in the 1986 papers when backprop was first introduced, the guidelines in the paper were, and I quote, set them to small random weights. That's not very helpful. Partly to deal with this 0 initialization problem, also partly because you want to break the symmetry a little bit such that different features get modified in different directions. But they didn't really have much guidance as to like, well, what does small mean? What does random, random from what distribution? What the hell? What are we going to do instead? So nowadays, people have generally consolidated on a couple different algorithms. I will note that there's sort of a little bit of an insight here that whatever it is, however it is that we initialize these weights, it should be somewhat dependent on the number of weights. Just simply because if you imagine that if each weight was some random number with some sort of Gaussian distribution, then if I have twice as many weights, or if I increase the number of weights, like if I'm like the sum input going into my next neuron is going to be something like, if you imagine each feature was set to 1, then the sum of all of those weights being added together is going to give you something that's sort of, if you add a bunch of Gaussians together, you get another Gaussian. But it'll have higher variance. And so if you're looking to have your the features at any particular layer have some sort of consistent variance, then you should probably have your weights be initialized based on the number of weights, or based on the number of inputs and outputs. There's a variety of different algorithms out there for doing exactly that. So some of them were named after Xavier Gloret, who, if we go all the way back, We've actually already seen his name out there. So again, University of Montreal, out of Joshua Bengio's lab. So this is a relatively recent technique to go ahead and pick what sort of weights to initialize from. And that technique is just simply, all right, you can either pick a uniform distribution in this sort of range where n is, so I'm initializing some particular weights, n is the number of layers in the number of features in the previous layer, m is the number of features in the post layer. So fine, that's an option. You can also do it as a normal distribution instead of a uniform distribution. There doesn't seem to be any particularly strong tendencies one way or the other. If you go and actually do the math here, it's all about trying to keep the variance the same across different layers. And then of course so that's one way of initializing. And there's another way of initializing is just look at the number of neurons or number of features in the output layer, and just base it on that. And that's called the initialization. Again, across based on yet another researcher. Again, from the same sort of time frame. These are the sorts of defaults. There isn't sort of strong differences between them. Basically all software tools are going to use one or the other of these initializations. PyTorch uses one as the default, and TensorFlow uses the other as the default. And of course you can swap back and forth. Not really a strong difference between any of these. But this will at least just give you some sort of decent initialization. It certainly is much better. So any of these initializations is much better than small random weights. But no really strong difference between these. Cool. Okay, that tells us how to initialize our weights. There's of course this question of like, well, will it always work? Will it always find the best set of weights? Even right in the very early papers, the comment was, hey, look, there is no guarantee. There might be local minimum. This gradient descent algorithm of just, well, decrease the error by slightly adjusting the weights. It's a complex enough function that there's no guarantee that there's one local minima. But then again, it's just sort of, by experience, it's like, oh, well, it just sort of generally works anyway. The experience with many tasks shows that the network very rarely gets stuck in poor local minima that are significantly worse than the global minimum. We've only encountered this undesirable behavior in networks that have just enough connections to perform the task. Adding a few more connections creates extra dimensions in the weight space, and these dimensions provide paths around the barriers to create poor local minima in the lower dimensional subspaces. What's being said there? Look, the worry is that you're going to have a task where, hey, all of your weight, it's doing okay at the task, but if I make a small change to any of the weights, it gets worse. But perhaps if I made a big change to a bunch of the weights, I could get an even bigger, a better solution to the task. That's the worry about getting stuck at a local minimum. The thing that's being pointed out here is, hey, if you have lots of weights, the chances of every single one of those weights making your task worse is pretty small. And so if even if you just add a few more weights, add a few more features, because whenever you add a feature, that's going to add a lot more weights. That's going to give the learning algorithm a little bit more flexibility, and it's unlikely to get stuck. That said, it might be slower to train. Okay, so what do we mean by all that? Will it always find the best set of weights? Not necessarily, but you can always just make the network a little bit bigger, and that's going to make it more likely to be able to find those big sets of weights. Trade-off, that of course is going to make it slower to train and slower to run, because you've made the network bigger, you've got more features. Practical matter, a lot of times what people will do is just sort of run it a few times and take the best result, because just, all right, it didn't learn well that time, let's just reinitialize it and try again. And you can use the same sorts of tricks with like validation data. rather than using the test data on that. So one of the interesting things you can also do, because this is sort of an iterative learning rule, is what you can do is you can say, okay, I'm going to train it on some part of my data. I'm going to hold out part of my data as sort of as my validation data. And I can just sort of, as I'm training on my training data, I can keep looking at the validation data. And if it starts getting worse on the validation data, all right, now we're sort of overfitting. We should stop now. Okay. So that's sort of a general technique. It gets called early stopping. Basically, you just do your training, but then as soon as the validation data starts getting worse, stop doing your training. Other small little tidbits. Terminology-wise, I just want to point out there's a slight weirdness in the learning rule that we've defined here. So this is the learning rule that we sort of described. It's all right, I have some training data, I have some target, I have my actual output. This is what I want to try to minimize. This is the error is sort of how wrong am I right now? And that's how I'm going to define up my learning rule. That's fine, but technically that's not what we want. I mean, really what I want is this is sort of the error on one particular point in my training data. Really what I want is a system that is good on all of my training data. So what I want to minimize the error on is the error of all of my different training examples. Okay? So in this sort of notation, so Z might be a three-dimensional vector, so my output is 3 dimensions, and that's indexed across K. So K takes on 1, 2, and 3. But I might have 1,000 different training examples, and that's my indexing N here. Right? And what I want to do is I want to minimize the error across all of those. Everything I've described so far, it's just sort of doing one at a time. It doesn't change the math at all. I could go ahead and go and derive all of the gradient descent and whatnot. It just means some sums show up. Doesn't actually change the form of everything because sums are just nice and linear. Terminology-wise, technically gradient descent, so if I'm trying to take my error, compute its gradient, and then adjust my weights to improve the error by just modifying, by going down the gradient, technically that should be this form here where it's across all of my training data. And this form up here where I'm just doing one at a time, that gets referred to as stochastic gradient descent, because it's sort of like, well, if I just look at one example, that's kind of like a really bad random approximation of this full one down here. It's just doing one at a time. So terminology-wise, this gets called stochastic gradient descent versus gradient descent. In practice, yes, this bottom one here would be better. It's just a little bit more computation to do. That said, what actually happens in practice is sort of a hybrid between the two. We want to do a bunch of samples at once, but there might be a lot of these samples. And so maybe you just take a chunk of the samples and compute them at once. And that's going to be, and what we call that is a mini batch stochastic gradient descent. So instead of doing one, we're going to do some number of them, where some number is whatever fits well on the hardware you're doing it on. Okay. So whatever size of this sum here fits nicely on the hardware you're running it on, that's what we'll do at once. Why would we, why is this the sort of hardware specific? This makes a huge difference in how quickly your algorithms run. Most hardware is much better at matrix multiplies rather than vector matrix multiplies. So being able to do this sum sort of on the fly, one way to think of this is these weights that sort of show up all over the place. I've got to actually go out and grab those weights from memory somewhere. It would be really nice if, once I grab those weights from memory, I can use them multiple times for multiple inputs. And so that's the particular, sum over this sort of n. Rather than grabbing the weights, doing a multiply, throwing it away, and then go grabbing the next weight, doing a multiply, throwing it away. So this is just purely an efficiency of implementation on hardware. And in particular, it starts turning out that on modern hardware, so much more of your time is spent on sort of accessing this memory to get your weights. It'd be real. There's a huge advantage to using the weights multiple times rather than just using the weight once, which is what we get in the pure sort of stochastic gradient descent version. So that ends up being just a huge optimization that just ends up being important for whatever. And so all of the sort of tools that let you do neural network or the sort of backpropagation learning will have some option that will be to control this mini batch. Okay, so basically everyone does this. Everyone does mini batch stochastic gradient descent, and you just set the batch to whatever works, efficient on the particular hardware that you have. Awesome. Other random small details to worry about this. One other thing that shows up whenever people are doing backprop is it turns out, and this was even right in the very, very, very first papers with backprop, the 1986 papers, that you don't even actually do the exact learning rule that we've been talking about here. So one of the problems with the learning rules that we've been looking at, where what you do is you take the derivative of the error with respect to the weight, and then you put a minus sign and some learning rule, and you say, okay, that's how some learning rate, alpha, and you say, okay, that's how I'm going to adjust my weight. Right. That's sort of the form of all the learning rules we looked at, including all of the backprop ones. That's how we derive the backprop learning rules. We're just actually doing this computation. And of course, you get this interesting thing about, do you want a large value here, or do you want a small value here? And of course, the worry is that with a small value, it'll learn very, very, very slowly. But with a big value, we're also going to learn really, really, really slowly, because it's going to sort of like, we're changing our weights too much each time. And one way to visualize what's going on here is what you can do is you can sort of imagine this space where, imagine there's only two weights, okay? And I'm going to plot that as weights this way and this way. So I've got weight 1 across this axis and weight 2 on this axis. And when I've got a particular set of weights, I'm going to be at some point in this space. And at each point in this space, there's going to be some amount of error. And the minimum of that error is, say, this point down here. And then what we're seeing here with these circles is this is sort of like a topological map. This is sort of like, okay, all of these values have about the same error. All of these values have about the same error. This is sort of like a big sort of valley in the weight space. And what we're trying to do is we're sort of initially having this set of weights, and then eventually over the learning rule, we should converge on the best set of weights. And what this picture is showing is, well, what happens with a learning route with a small, if I have a small learning rate, so this alpha parameter is very small. If I'm here, if I'm at this point, what the learning rule says is take the derivative of my error surface and change my weights in that direction. And so we're visually depicting that process here. What does this minus alpha sort of process mean? Well, that means take this weight, go perpendicular to this curve, and do a small step. Perpendicular curve, do a small step, small step, small step, small step, small step, and then eventually we'll get there. But if I have a big learning rate, I say there, okay, go perpendicular to the curve, maybe I'll overshoot. And then maybe I'll overshoot again, and then maybe I'll overshoot again, and overshoot, 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 overshoot. So this is large learning rate still takes a long time to learn. So because this is sort of known, and because it was like, it was really hard to go ahead and figure out what a good weight is, one thing that was sort of defined right early on again in the 1986 papers, and is sort of a very common thing, is, well, you know what? Whenever we modify our weight, let's sort of smooth that data out a little bit. So instead of just modifying my weight based on what this derivative is, fine, keep that part. That part there, it's the same as that part there. So fine, that's going to be my weight. But also, however I changed my weight on the previous update, do some in that direction as well. So whatever my weight update was on my last time step, okay, keep updating in that direction as well, but sort of scaled down a little bit. Okay. So the what this can be thought of is this is going to be thought of as thinking of as, hey, as we're moving around in this space, have some sort of momentum. So whatever change I make in the past, assume it's probably still a good direction to be changing things in. And it just sort of turns out that this seems to be a nice compromise and sort of gives you a nice smooth, or at least can make it a lot easier to sort of find an optimal value across a pretty wide range of spaces. So again, pretty much all of these neural network learning rules will also have this momentum parameter. But now we have two parameters. Now we've got to optimize two different things. We've got to optimize both the learning rate and this momentum parameter, how much to include the old weights. So you end up still having these parameters to play with. And again, sometimes it works well, sometimes it doesn't. Now we've got to play with these things. It's very aggravating. Fortunately, again, modern techniques have sort of pointed out, by modern techniques I mean 2015, there's sort of a standard that people have now settled on called ADAM, adaptive moment estimation. So basically it's doing this sort of trick, but it's sort of on the fly figuring out good scaling factors for even, for this learning rate, for all of these sorts of things. Among other things, it's also sort of indicating it ends up using a different learning rate for each parameter, because there's nothing says that I should have exactly the same learning rate on every single one of my weights. Especially weights at different parts of the network maybe want very different learning rates. So it ends up adjusting that learning rate based on the first and second moment of the gradient. Tons of wacky details if people care about implementing that. Again, no one really implements it. It's just built into the tools you use. The overall result is, hey, ADAM just ends up being so much less reliant on tuning the learning rate that just everyone should just use it and go ahead and just do that. So again, this is one of those things where in the past you would spend a lot more time playing around with the learning rates and momentum parameters. Nowadays, just use this. Everything's fine. All right. Other last minute things to talk about. Always, whenever you're building one of these networks, yes, it's going to go ahead and learn its own features, but you still have to decide how to feed your data into the network. Okay? You're still going to make interesting choices there. If you have categorical data, like, I don't know, all this sort of people and relationships in family trees, pretty much the default to use is just do one hot encoding. Just turn that into a set of inputs and set one of them to a 1. Just use one hot encoding. That's a relatively safe bet to go with. Things do get more complicated than that. One of the sort of early on, again, another sort of thing people have done with these neural networks, and we'll talk a lot more in the next lecture, is playing games. And I just wanted to do this as an example of a very complicated input representation. So for example, in 1989, there was this NeuroGammon, which was basically, let's get a neural network to learn what the best move is in backgammon. And we'll do this just simply by, here's a whole bunch of training data about people playing backgammon and what they did. So go ahead and train up that network. There's also another version that sort of learned by playing against itself. Again, we'll talk about that next time. But the thing I wanted to point out here is, how did they end up doing this sort of input representation? Again, we have this situation where, all right, so it's the game of backgammon. There's like little pieces on all sorts of that could be at different locations. There's different numbers at different pieces. And you've got to come up with some way of converting that into inputs to your network. Yes, in theory, you could just pick any way you wanted, and then as long as you've got enough hidden units, it'll learn new features based on that. I mean, that was supposed to be the whole promise of this learning of features, is I don't have to figure out what the best features are for this task. It can learn it itself. However, it's pretty much always the case that by making different choices about how you feed, how you are going to feed this data into the network, you're always going to you can make the task easier or harder by playing with that input. For this sort of neural network that's representing this particular game, there ended up being this, well, perhaps relatively complicated. So again, the particular way that they did this, for each point in the backgammon board, of which there's a whole bunch of what is there? There's 6, 12, 24 points on the backgammon board. For each point, I'm going to have 4 input units that indicate the number of white pieces. If there's no white pieces, all those before values were set to 0. If there's 1, then set one of them to a 1. If there's 2, set the first 2 to a 1. If there's 3 or more, set the first 3 to a 1. And then the 4th unit, if there's more than 3 pieces, the 4th unit came on indicated to a degree indicating the number of additional pieces beyond 3, where it's n over 3 or n minus 3 divided by 2, and that was how we indicated more and more, because you can have many pieces on a single square. And then you did 4 of those for white, 4 of those for black for each of the 24 points. That gives 192 inputs. And then there's additional units for the number of white and black pieces that are in the sort of middle space. 2 more for how many pieces already had been taken off the board. And then 2 inputs indicating whose turn it is. And then I love this particular statement. They went through that bizarre long process, and they say the general logic behind these choices should be clear. The idea there, they wanted there's simpler ways to do that, but the idea here is trying to represent the position in a straightforward way. Didn't really attempt to minimize the number of units, but wanted to set things up so that conceptually distinct situations were represented in separate ways. Important, and this is sort of a situation where knowing the rules of backgammon became really important, because having one individual piece on a point on its own is a very different situation in backgammon to having 2, and so they wanted a very different way of indicating that. But having 5 versus 6 points or pieces on the same point, not a huge difference in strategy. So that means that there was relatively small difference in the input for the situations like that. So they were still hand designing these features to a certain degree, and it's still kind of important to worry about that input representation. But the hope is, at least given these different input representations, neural networks can still learn good features. You can simplify the task of the network tremendously by giving it good features. Even though the whole point of this whole backprop thing is that, in theory, it should be able to figure out its own features. It's still a good idea to make the job of the networks making these features as easy as possible. All right. Very, very, very last thing I wanted to say about this whole backprop thing. Yes, fine. It sort of works in lots and lots of situations. It was very, very biologically inspired. These neural networks, these multi-layer neural networks, were definitely inspired by brains, and that very naturally leads to the question of, well, could this learning rule that we've derived, could that be a learning rule that's actually physically in real brains? And certainly the learning rule over here, that seems pretty possible. But there's sort of a general worry about the learning rule for these weights here. And that the learning rule for these weights here, if we could sort of write out what backprop says, these weights here, in order to figure out how to adjust them, we need to know what these weights here are. Now, adjusting the learning rate, adjusting the weights does seem to be something, in real brains, there are connections between neurons, and those connections between neurons do grow and shrink, and the size of them does indicate how strong, some sort of connection from one input to the other. So there are things like weights in the brain. But the worry is, so there's things like weights, and there are things that adjust those weights in real brains. The worry is there doesn't seem to be a good way of, if there's actually a physical connection between these neurons, and that's like a physical connection in the real brain, there doesn't seem to be a good way of that physical connection knowing what this weight is in order to figure out how it should adjust this. So this is known as the weight transport problem. How do you transmit that information? There's a bunch of different possibilities that are out there in literature. People sort of tried to explore, can you get close to that in real brains? There's all sorts of interesting sort of. First of all, it doesn't seem obvious any sort of direct, clear way to do this. But there's been some interesting suggestions of alternatives. The most sort of one particularly fascinating one that I love is this variant of backpropagation called feedback alignment. That sort of came out of, they were implementing backprop, they were implementing this particular algorithm, and then there was like, they messed up the code, and this weight here, instead of setting it to be the correct values, they set it to be just a random set of weights that were never updated and just were fixed and changed, and fixed and never changed, and it was just some random set of weights. And it worked pretty good. It's not quite as good as backprop, but it still works pretty good. There's a bunch of interesting theory about why that is the case. One interesting caveat in there, one thing to keep in mind if you're ever implementing backprop yourself, it is really easy to mess up implementing backprop, and still the resulting algorithm still vaguely works, which is frustrating. And this is sort of an extreme example of that. In any case, there are definitely possibilities that maybe you don't need to do exactly backprop. Maybe you can do something close to backprop, and maybe that might be what the brain is doing. But this particular algorithm, as defined here, is sort of like the ideal optimal algorithm if you've got full access to all the information. It might be that brains just are not going to have access. This particular connection here is not going to have access to this weight here. And so maybe it's got to do something slightly different. Cool. All right. What was the point of all of that? Yes, backprop is really, really cool. You can find features by starting with random features and then improving them. And just by following this backprop learning rule of take the derivative of the error, and that tells you how to change the features. This general method works for many, many, many different network structures, just anything. In fact, it doesn't even have to be networks. It's just anything I can take the derivative of. As long as my error is something I can take the derivative of, as long as my network, the things that I'm doing to compute features, as long as those are things that I can take derivatives of, this should all still work. I can add other things into the loss function. I can maybe minimize weights, which is something that keeps showing up in other sorts of systems, right? In the SVM, we also minimize the magnitude of the weights. We could add that into the loss function and include that. We could do things other than multi-layer perceptrons. We could do just any sort of other math that we wanted to fit in there. We could do that. But a really, really standard thing to do is this multi-layer perceptron thing. In practice, use the ReLU activation function. Use Atom to control the learning rate. Use one of the built-in initialization methods in order to initialize the weights. With those sorts of constraints, there's still sort of this open question about, well, how many features do you have in each layer? How many layers? And that just tends to be, try it out. Start small. If it doesn't work well, make it bigger. That sort of general heuristic is hopefully enough to sort of build up these networks, and at least we don't. At least with things like we can at least fine use the ReLU activation function, use these initializations, use Atom. That helps a lot with making it less of a blind search, but it's still hard to know exactly the sort of size of network and what you might need. All right, thank you very much. That's Backprop. In the next lecture, we're going to go start talking about things like applying this to playing games and reinforcement learning. So we will see you then. Thanks. Bye.